Well, good evening or morning or afternoon, whenever you have found the time. This is chapter 9, Reasoning and Proof. This chapter could take us the entire year, or in this case, one day. Um, what we're going to do is kind of just throw a lot at you, and then throughout the next month and a half of school, given the opportunity, we'll grasp it and really show you exactly why it works and what it works. There's a lot going on here on this sheet. Um, and you've seen a lot of this, but you've never really been held responsible. So we're going to be really kind of going off this proof by deduction or direct proof, and proof by contradiction. We'll add another type of proof called proof by induction, but guess what? That gets its own chapter. That's chapter 10. So let's take a look at what they mean by some of these proofs. Hey, proofs don't always have to be like, all these words, and sometimes they're just pictures. So let's say we take this right triangle. Sorry, I didn't put a right triangle in there. And I don't know, maybe we copy it and rotate it and kind of put those two together like that. Copy and rotate it, maybe something like that. And copy and rotate. That's pretty cool. So what we might look at is what happened. Well, uh, maybe we label this side C, so that would be C. We could do a little bit of math, and we could prove that these are all 90 degrees. So the area of that white square inside is C squared. Mr. Sayers, you're amazing. How did you even? All right, so I thought that was so cool. I made a duplicate. And what I'm going to do here is I'm going to drag some stuff. I'm going to drag this up. Oh, no, no. Let's go ahead and capture this in a square. Oh, all right, that's kind of messed up. Let's see if I can go backwards, and I can't. All right, try that again. Here we got it reset. So what we're going to do is this is the same picture, but we're going to draw that up to that, and let's go ahead and pull this to here, and this down here. So what do we have? Uh, since this is a square, that is going to be our good friend a squared. And this is b by b, so that's b squared. Ladies and gentlemen, the white area in both pictures are the same. So a squared plus b squared is equal to c squared. That is one of 365 different proofs in this guy's book about proofs of the Pythagorean theorem. Pretty cool. All right. Hey, so this is where people go wrong right away on proof, and they don't give themselves the opportunity to tell the world, hey, you know what? I know I can rewrite an even number. And you're like, 4. But you got to write it in more general terms. So we'll say n is even if we can say it's 2 times some number, and that number has to be an integer. So if I wanted to prove that the number 100 is even, I need to show that it's 2 times some integer, and that integer turns out to be 50. Okay, so odd means that I can rewrite it as 2k, and even plus 1. So every time you see odd, you need to think about 2k plus 1. And finally, that is divisible by any number m. And that's just like 100. If I wanted to, say that, oh, this quantity 3 um, L plus Z is divisible by 3, I need to show it equals 3 times K, where K is any integer. Positive or negative, 0 doesn't matter. 3 times. Here's a quick little proof. Sometimes you just have these in your back pocket. They work out. Prove that 0.3 repeating is irrational. What is irrational? It is P over Q, where P and Q are integers. Integers. So there you go. And you have to mention that Q cannot be equal to 0. Bottom number cannot be equal to 0. So how can I write 0.3 repeating? So that's 0.13, 13, 13 on forever. Well, the way I like to do it Just write it like that. Since I have two decimal places here, I'm going to multiply both sides by 100. Multiply this by 100, I get 13.13 repeating. I'm going to subtract off 1x from both sides. So I get 99x equals, well, x might, I don't know, but look what x equals. It equals that 0.3 repeating. So it's going to cancel that out, and we're going to get 13. So x is equal to 13/99. Pretty cool. You try it. 0.159 repeating. How could I write that as a repeated or a rational number? Well, boom, there you go. You gave it a shot. You should have multiplied by 1,000 both sides, subtracted 1, so you got 159 over 999. That is exactly the same thing as 0.159 repeating. Pretty cool. All right, so 4, 5, 6, 7, 8, 9. In a perfect world, you'd be like, oh, Mr. Sayers, I got this. This is no problem. Well, it is a problem because you've never done these problems before. So it's like, how do you prove this? So prove that the difference between any two rational numbers is also a rational number. Well, if you don't know what a rational number is, don't start this problem. Go to the next problem. But I think we just talked about it, so you have a shot. Let's look at it. So first of all, you got to kind of define some things. All right. So we let x and y be rational numbers. They give it a quick little definition. Why not? Why not tell the world what the p, the q, the r, and the s is? All I know at this stage is those are all integers, and q and s cannot be equal to 0. That's all I know. Now this says the difference. Well, I think that's subtraction. So we do x minus y, we plug it in, we add like term, or like we get common denominator, and we end up like this. The proof is now the question is this a rational number? And what do you have to show if it's rational? The top has to be an integer and the bottom has to be an integer. Well, in most worlds, if you take an integer times an integer, you get an integer. Integer times an integer, integer. And when you subtract integers, you get an integer. So the top's an integer. Mr. Sayers, that is a weird proof, but it's correct. What about q times s? Is that an integer? Absolutely. Oh, but man, what if it's equal to 0? That would really stink. Well, guess what? We know that Q and S, either one of those can't be 0, so we're in the clear. Let's see how they wrote it. Oh, they kind of did. They wrote it out like verbally. So that, ladies and gentlemen, is fine. All right, tonight, I'm going to have you kind of mess around with some of these other ones. Prove that the product of any two rational numbers. So that's probably following that. Prove that the product of two odd integers is odd. I would know this one inside and out. We just talked about what an odd number is. Why don't you multiply them out and see what you get? See if it fits. Divisible by 8. Hey, the hint here is what you need to do is you need to somehow show that if I take two squares of odd integers, I'm going to get 8 times an integer, where k is an integer. So maybe you try to multiply those out, factor out an 8. If you've got all these integers on that side, that's going to work out just fine. I'm not going to read the answers to you, but I've included all of them. So this is something that maybe I would suggest that you start these problems. Just start them and then see how they put them. If you just read them, then I think it's going to go in one ear and out the other. So there I have 4, 5, 7, 8. So on the notes, you have all those. Disproof by counterexample. People don't realize how important it is. If somebody says something really cool, but I find one instance that it doesn't work, it's not a true statement. So it's very important to understand that prove that it works or it doesn't work. If you can find one instant doesn't work, that's what life's all about. So let's look at a very famous one. Somebody thought they had come up with an equation that pumped out all the prime numbers. And if you do, you plug in 3, you get 47. prime. If you plug in 7, 83, prime. If you plug in 10, 131, prime. So guess what? People say, oh, it works. But I think I can plug in something so that, remember, prime is a number that's only divisible by 1 and itself. So, and when you say itself, you're implying that it's different than 1, okay? Because 1 is not a prime number. All right, shoot. Well, since I know the answer to this, I'm going to try n equals 41. So I get 41 squared minus 41 plus 41. Guess what? I know that that is divisible by 41. Okay, so it doesn't work. Mr. Shades, you can't pick. Yeah, I can pick anything I want. It says n is any natural number. Natural numbers 0, 1, 2, 3, 4. Plug it in. No, it doesn't work. So maybe a little simpler. Hey, they think this works. Well, I'm going to let a equal to 2 and b equal to 3. So 2 plus 3 squared, does that equal 2 squared plus 3 squared? The answer is no. 4 plus 9 is 13. So it may work for other numbers, a and b, but it doesn't work for 2 and 3, so no way. If p is prime, then 2p plus 1 is prime. Well, let's pick some prime numbers and plug them in. 2, 3, we don't have to, I'm sure that's going to work. So 4, 5, darn, that's prime. 7, darn, that's prime. 11, hey, maybe this works. Let's just say it works. I bet it just works. Well, we'll try one more. 14, 15. Darn, doesn't work. All right. So if we say find a counterexample doesn't work, it probably doesn't work. Maybe you have to try a few numbers before it works. Proof by the contrapositive. Gosh, I just think this is amazing. This is, if you guys like Alice in Wonderland, Lewis Carroll's the pen name of, man, he was a professor at Oxford, mathematician, and he would write these little lyrics that would use logic, mathematical logic, that you'd have to use contrapositives, combine the statements, and voila. Maybe some of you saw in geometry the idea of she's a witch with Monty Python, Holy Grail. That whole logical sequence comes from, that's what Lewis Carroll loved. So contrapositive, if A, then B, is rewritten not B, then not A. So that's how you interpret that. Let's look at a quick example. I really can't spend too much time. I really don't think this is something that's going to be hit, but it's so amazing. So let n be an integer, prove that if this is true, then this is true. So we have the hypothesis and the conclusion. So what does the contrapositive? Oh, and the beautiful thing about contrapositive is the original statement and the contrapositive, which I'll write right now. So the contrapositive is you switch and you negate. So if n is even, then n squared minus 4n plus 5 is odd. That's negating it. That's saying the opposite of what they're saying. We are still remembering that n is an integer. So maybe this might be easier to prove. And if this is true, that means the original or the contrapositive of it is also true. Very cool, very powerful. So if n is equal to n is even, I maybe write something like this, or k is an integer. I'd plug it in. We get 2k squared minus 4 times 2k plus 5. And a lot of this is, where am I going with this, Sayers? What you want to show is that you can get an even number plus 1. That would make this odd. And I hope you can see that we are really close already. 4k squared minus 8k plus 4 plus 1. Really weird that I did that, but I can factor out my 2. I get 2k squared minus 4k plus 2 plus 1. This is an integer. 2 times an integer is an even integer, plus 1 makes it an odd integer. You're done. All right. I wanted to bring your attention to example 8. I would highly recommend you listen to that self-tutor. They walk through it very nicely. This is a great proof by contrapositive, but it includes notation. You know, they tell you what it is. You just have to kind of try it. Try it on for size. I'm not going to take the time right now. Okay, proof by contradiction. This is something you're definitely going to be asked to do. It's cool to say it in Latin. Reductio ad absurdum. I feel like some ghost from Harry Potter is going to come out, but nope. We start with the negation of the conclusion. So we just assume the opposite is going to happen. And what we need to do is show that creates a ridiculous situation. So best way to do this is show you an example. Prove that there are infinitely many prime numbers. Okay, so we want to prove that something that we can't see or feel or taste or touch. So that's pretty hard. So what we're going to do is start out with the opposite. Suppose there are a finite number of prime numbers. So now we can count them. So that means we can label them. P sub 1 is the first one, that'd be 2. P sub 2 would be the second one, that'd be 3, and so forth. But this one is the last one. Well, that would have to be true if there are a finite number of prime numbers. So now from the opposition, we have to do step-by-step logical steps. Well, great. Every positive integer greater than 1 is either a member of the list or divisible by a member of the list. That makes sense. All right, so capital N, now what we're going to do is multiply all of the prime numbers together. So 2 times 3 times 5 times 7 times 11 times 13, all those. And then we're going to add 1 to it at the very end. All right, notice that this N, this number, is going to be bigger than any single prime number. Okay, so in other words, there's no way that this capital N is part of this list. That makes sense. All right. Now, if we divide N by any number, any of the prime numbers, it's not going to go in nicely. Right? There's always going to be a remainder of 1. Okay, always, because it's just, yeah, you just have to think about it. And so, but wait a minute. If we have a number that can't be divided by any prime number before it, then that makes itself a prime number. So this is the statement that says nothing goes into it, therefore it's not divisible by any prime number, but we said there were no more prime numbers, but obviously this is the next prime number, so this is a contradiction. So our supposition is false, and therefore you state the opposite of your supposition. All right. Prove the log base 2 of 3 is irrational. 2 to some number equals 3. Remember, 2 to something equals 3. We're saying that this number is a rational number, or I'm sorry, is irrational. So what's the contradiction? Let's say it's rational. Okay, well that means this is true. It has to be true if it's rational. And look, they restate what rational number is. I don't think you really need to do that. Okay, so if you rewrite this in exponential mode, 3 equals 2 to the p over q. You take both sides to the q, and you get 3 to the q equals 2 to the p. Right? What we're trying to do is reach something that's impossible. Reach something that's impossible. The left side is always odd. 3 times 3 is 9, times 3 is 27. It's always going to be an odd number, because an odd times an odd will always be an odd. An even times an even will always be an even. So just the fact that that side is odd and that side is even means there's no way those can equal. Therefore, we've reached a contradiction. That means we now have to say that that is doesn't work. So what is the opposite? The opposite is this, and we're good to go. Strange. It's like a weird new pair of shoes. You got to try them on, walk them around for a while. All right. Example 10 is just a famous one from Pythagoras' days. They say somebody was killed because they proved this is correct, but by doing so, it got rid of all their beliefs that everything could be written as with integers. So it messed people up. So what do? You throw them overboard. 3, 4, 5, 13, 14, 15 are all proof by contradictions. So what you'll do is you'll try to say the opposite. I'm not asking you to do these, like get them start to finish, but I'm asking them to start and then work through the solutions and see how, are you close? Are you making sense of it? What is the goal? What is the goal? Too often in math, you just keep working until you get an answer. In proof, you kind of have to know what that answer must look like in order, you can't falsify and get it, and erase some stuff, but you kind of have an idea of where you need to go, and that's what makes it challenging and fun. I'm going to do number 3 for you. I like number 3. Prove that A is less than B. So there's my if, and then the then is that must be true. So in a direct proof, we start with our supposition, and what we're trying to do is work down to our conclusion. I love this step. It's like, how am I supposed to start here and end here? Well, there's a to, there's a be, there's a lot of things you have to introduce. The way you introduce that is legal steps. Can you add a to both sides? Absolutely. Does it switch the sign? No way. So then we get 2a equals a plus b on this side. Then we're going to divide by 2. Does that switch the sign? No, it's a positive 2. So did we end up where we wanted to? You bet. You bet. The proof by contradiction, if you're like, hey, no, I'm good with that one, that's neat, but proof by contradiction is automatically, you know this is true, and you want to get here, so you suppose the opposite is true. So the opposition here is greater than or equal to that. Well, what happens then? You kind of work it. What your goal is to come up with something that can't be true. We know this is true. So wouldn't it be cool to come up with something that kind of was contradicted that? So here we're going to multiply by 2. That's fair. Subtract a. That's fair. And you see that we end up with a is greater than or equal to b, which is a direct contradiction to what we know is true. Therefore, that's a contradiction. The opposite must be true. Cool. All right, there's a bunch of answers. This is chapter 9 in one day. And so, sure, we'll do some in class tomorrow, but I'm just trying to set the tone of proof a little bit. We will do chapter 10 very thoroughly. Thank you.